Hello my friends, and welcome back to Sky Creative Channel. Today, we're witnessing craftsmanship and technology unite in ways that would have amazed the industrial pioneers of yesterday. From molten steel to precision machinery, let's get started. We're stepping into the world of ArcelorMittal, the steel giant that's been shaping our world since 2006, though its roots stretch back much further into the golden age of American industry. You know, steel production has come a long way from those roaring blast furnaces of the 1950s, and what we're about to see is nothing short of remarkable. And ArcelorMittal's sustainable steel production begins at the electric arc furnace, or EAF for short. Now, this isn't your grandfather's steelmaking method, though he'd certainly appreciate the innovation. The EAF uses massive graphite electrodes that can reach temperatures of 3,000 degrees Fahrenheit, hot enough to melt scrap steel and turn it into liquid gold, or rather, liquid steel. These electrodes create an electrical arc, similar to a lightning bolt, that generates intense heat. The beauty here is that they're recycling up to 90% scrap metal, making this process remarkably sustainable. Once melted, the steel flows into a ladle furnace system where the real magic happens. Here, precise alloying takes place. Computer-controlled systems add exact amounts of elements like manganese, chromium, and nickel, measured down to fractions of a percent. Think of it like a master chef perfecting a recipe, except this recipe needs to meet ISO 9001 quality standards. The ladle furnace also features argon stirring technology, which bubbles argon gas through the molten steel to ensure uniform composition and remove impurities. Next comes the continuous casting machine, a marvel of engineering that would astound the steelworkers of yesteryear. The molten steel, still glowing orange at around 2500 degrees, pours into a water-cooled copper mold. As it descends through the machine, powerful water spray systems cool the steel at precisely controlled rates. The continuous caster can produce steel slabs up to 12 inches thick and 80 inches wide, moving at speeds of up to 20 feet per minute. Electromagnetic stirring systems ensure the internal structure remains flawless. NNTHE final stage involves the hot strip mill, where those massive slabs are transformed into coils. The roughing mill reduces thickness through a series of powerful rolling stands, each applying thousands of tons of pressure. Then the finishing mill, with its 7 stands of 4 high rolling mills, brings the steel down to its final thickness, sometimes as thin as a few millimeters. Advanced laser gauges continuously monitor thickness to tolerances of just 0.001 inches. The steel then travels through cooling beds, where computer-controlled water jets bring it to the perfect temperature before coiling machines wind it into those massive coils you see shipping worldwide. This entire process, from scrap to finished coil, represents over 150 years of steelmaking evolution, now perfected for the 21st century. Let's head over to Italy, where Cymex Engineering has been crafting heavy-duty construction equipment since 1992. Now, folks who remember the post-war construction boom will appreciate how far we've come in manufacturing precision. Today, we're watching them produce shafts for their CBE crusher bucket line, equipment tough enough to tear through concrete and rock. NTHE process starts with selecting premium alloy steel billets, typically 42 CR-MO4 steel, known for its exceptional strength and wear resistance. These raw billets enter a CNC turning center, specifically a heavy-duty horizontal lathe with a swing capacity of up to 800 millimeters. The lathe's carbide tip cutting tools, spinning at precisely controlled speeds, rough out the basic shaft geometry. Coolant floods the cutting zone at 20 gallons per minute, keeping temperatures stable and washing away chips. This initial roughing operation removes material at rates of up to 500 cubic centimeters per minute. Next, the shaft moves to a specialized heat treatment furnace, where it undergoes through hardening at 850 degrees Celsius, followed by oil quenching. This process, perfected over decades of metallurgical science, transforms the steel's internal structure, achieving hardness levels of 28 to 32 HRC on the Rockwell scale. After tempering to relieve internal stresses, the shaft is ready for precision machining. Now here's where it gets fascinating: the OP-19 crankshaft pin roughing operation. The crankshaft, a component that's been fundamental to rotating machinery since the Industrial Revolution, requires extraordinary precision. The workpiece mounts on a specialized crankshaft grinding machine with adjustable centers. High-speed grinding wheels, made from aluminum oxide abrasive, spin at 2,000 RPM, while the crankshaft rotates at a much slower speed. The grinding wheel makes multiple passes, removing material in cuts of just 0.010 inches per pass. What's remarkable is the machine's ability to grind the offset journals, those eccentric sections that create the engine's stroke, while maintaining concentricity within 0.0001 inches. NTH EOP 110 operation represents the pinnacle of precision machining, fine machining of the flange, pin, and flange bearing surfaces. Here, we're talking about a multi-axis CNC machining center, equipped with ceramic cutting tools that can maintain sharp edges even at high temperatures. The machine's automatic tool changer swaps between end mills, boring bars, and finishing tools in seconds. For the flange face, a fly cutter creates a mirror-smooth surface finish measured in microinches. That's millionths of an inch, folks. NTHE pin machining uses a technique called interrupted cutting, where the tool periodically breaks contact with the surface, preventing heat buildup. Meanwhile, the bearing surfaces undergo a honing process, using diamond-impregnated stones that oscillate while rotating, creating a crosshatch pattern that's perfect for oil retention. Throughout this operation, laser micrometers continuously measure dimensions, feeding data back to the CNC controller, which adjusts tool positions in real time. This level of precision ensures these crankshafts will run smoothly for thousands of hours under extreme loads. All aboard for a trip to Lucchini RS in Italy, a company whose railway wheel legacy goes back to 1883. That's right, when the Transcontinental Railroad was still relatively new. If you rode trains in your younger years, you were likely rolling on wheels made through processes descended from these very techniques. NTHE journey begins with the electric arc furnace, where premium scrap steel melts alongside carefully selected alloying elements. Lucchini's special steel formula, designated as ER8 grade, contains precise amounts of carbon, manganese, and silicon, a recipe refined over 140 years of wheel-making expertise. The molten steel, at 900 degrees Fahrenheit, pours into preheated ladles where vacuum degassing removes trapped gases that could weaken the final product. And from there, we move to the ingot casting station, where the steel solidifies in massive molds, creating ingots weighing several tons. These ingots then enter a remarkable piece of equipment called a rotary forging press. Picture a machine that can exert 10,000 tons of force, that's equivalent to the weight of 70 fully loaded semi-trucks, all focused on shaping that glowing steel ingot. The press literally squashes the ingot into a rough wheel shape while it's still red hot, a process that aligns the steel's grain structure for maximum strength. Next comes the hot rolling mill, where the real wheel shape emerges. The rough forging travels through a series of specialized rolling dies that gradually form the wheel's profile, the tread, the rim, and that distinctive curved plate connecting to the hub. During this process, the steel temperature must stay above 800 degrees Fahrenheit. Drop below that, and the steel becomes too stiff to shape properly. Infrared sensors constantly monitor temperature while automated systems control the rolling sequence. And after forming, each wheel undergoes a critical heat treatment process. They're placed in a special furnace for controlled cooling, what metallurgists call normalizing. This isn't your everyday cooling. The wheels cool at precisely regulated rates to achieve the perfect balance of hardness and toughness. The rim needs to be hard enough to resist wear from millions of wheel rail contact cycles, while the center plate must remain tough enough to absorb shock loads. NTHE final machining stage is where precision meets performance. CNC vertical lathes, with cutting diameters exceeding 6 feet, machine the wheel to exact specifications. The tread profile is cut to tolerances of 0.020 inches, ensuring perfect contact with the rail. The bore gets precision machined to fit the axle with an interference fit, meaning it's actually slightly smaller than the axle, so when pressed on with hundreds of tons of force, it creates an incredibly strong connection. Finally, ultrasonic testing equipment scans every wheel, sending sound waves through the steel to detect any internal flaws invisible to the human eye. Only wheels that pass this rigorous inspection earn the right to carry passengers and freight along the rails. Setting sail with Sino Output Group in China, we're diving into the fascinating world of marine propeller manufacturing. You know, propeller technology hasn't changed fundamentally since the 1830s, but the manufacturing precision certainly has. NTHE process starts with pattern making, where skilled craftsmen create exact wooden or resin models of the propeller blades. These patterns must account for something called shrinkage allowance. As molten metal cools, it contracts by about 2%, so the pattern is made slightly oversized. This age-old technique still guides modern foundry work. Next, we enter the molding department, where the sand casting process unfolds. Workers create a mold using special green sand, a mixture of silica sand, clay, and water that holds its shape perfectly. The pattern gets pressed into the sand, creating a perfect negative impression. For large propellers, this might require molds weighing several tons. Flask boxes, those metal frames holding everything together, ensure the mold halves align precisely. NTHE real drama happens at the melting furnace. Sino Output typically uses nickel aluminum bronze alloy, designated as NAB or CEAL 10Ne5 Fe4. This special bronze, melted at 950 degrees Fahrenheit, offers superior corrosion resistance to seawater, crucial for equipment that'll spend decades underwater. The molten bronze pours through a gating system designed to fill the mold smoothly, preventing air entrapment that could create weak spots. And after cooling for several hours, the casting emerges rough and covered in sand. Now begins the precision machining phase. CNC, 5-axis milling machines, equipped with computer models of the perfect propeller geometry, mill each blade's complex curved surfaces. These curves aren't random. They're based on hydrodynamic calculations, ensuring maximum thrust with minimum cavitation. The blade pitch, thickness, and trailing edge all get machined to tolerances of 0.040 inches. Finally, the hub bore is precision machined to fit the propeller shaft, and the entire propeller undergoes dynamic balancing on specialized equipment that spins it while measuring vibration. A perfectly balanced propeller ensures smooth operation and extends shaft-bearing life by years. High in the Alps, we're witnessing something truly special, the cable splicing operation for the Panoramabahn gondola lift. Cable car technology dates back to the 1860s, but the engineering precision we're seeing here would astound those Victorian-era pioneers. NTHE main haul rope, typically 50 millimeters in diameter, consists of 6 strands wrapped around a fiber core, similar to cables used in the Golden Gate Bridge. Each strand contains multiple steel wires, giving the cable incredible strength, often exceeding 200 tons breaking strength, while remaining flexible enough to bend around sheave wheels. NTHE splicing process begins with careful preparation. Technicians unwind the cable ends for several feet, exposing individual strands. Using specialized hydraulic cutters, they trim each strand to precise, staggered lengths. This is called a long splice, and it's crucial that no joints align, which would create a weak point. Think of it like how bricklayers stagger brick joints for strength. Next comes the intricate weaving process. Working with cables under tension requires specialized rigging equipment, including come-alongs and cable grips rated for the massive loads involved. Technicians interweave the strands from each cable end, tucking new strands where old ones were removed. This requires both strength and finesse. Each strand must be pulled tight and positioned exactly right. Once interwoven, the splice gets served, wrapped tightly with galvanized wire using a specialized tool that maintains consistent tension. This serving protects the splice and ensures it passes smoothly over the sheave wheels in each tower. And finally, the spliced cable undergoes load testing using hydraulic tensioning equipment. This meticulous work ensures millions of safe trips for skiers and sightseers for decades to come. Welcome to Diamond Plastics Corporation, where they've been revolutionizing pipeline technology since 1982. Now, if you remember when most pipes were made of cast iron or clay, you'll appreciate how PVC transformed infrastructure, lighter, longer lasting, and immune to corrosion. This operation produces massive 54-inch diameter PVC pipes using a process called continuous extrusion. It starts at the material handling system, where polyvinyl chloride resin arrives in pellet form. These aren't just any pellets. They're compounded with heat stabilizers, impact modifiers, and processing aids that give the pipe its legendary durability. Automated systems blend these ingredients in precise ratios, typically around 3% additives to 97% PVC resin. NTHE blended material feeds into a massive twin-screw extruder, the heart of the operation. This machine is a beast. Imagine a barrel 20 feet long with two intermeshing screws rotating inside. As the PVC travels down the barrel, multiple heating zones gradually raise the temperature to around 400 degrees Fahrenheit, melting the plastic into a homogeneous melt. The twin-screw design provides superior mixing compared to older single-screw extruders, ensuring consistent material properties throughout. Here's where it gets impressive. The molten PVC exits through an enormous die head, a precision-machined steel ring that shapes the pipe's profile. For a 54-inch pipe, this die might weigh over a ton. The die includes internal mandrels and external rings, creating both the inside and outside diameters simultaneously. Die design is critical. It must account for die swell, where plastic expands slightly after leaving the die, and ensure even flow distribution around the entire circumference. And as the pipe emerges, it enters a vacuum sizing tank system. Picture a long water-filled tank, maybe 30 feet long, containing sizing sleeves. Vacuum ports around these sleeves pull the soft plastic tightly against the sizing forms, while cold water cools it. The pipe travels through multiple tanks, each progressively cooling and solidifying the PVC. Cooling rate control is crucial. Too fast, and internal stresses develop. Too slow, and the pipe might deform under its own weight. NTHE pipe then enters the spray cooling section, where mist nozzles provide additional cooling while the pipe gains rigidity. Finally, it reaches the haul-off unit, a specialized Caterpillar track system with rubber belts that gently grip the pipe, pulling it through the line at speeds around 3 feet per minute. NTHE final station is the automated saw, which cuts pipes to standard 20-foot lengths. These cuts must be perfectly square, within 1 degree, to ensure proper bell and spigot joint assembly in the field. These pipes, meeting ASTM D3034 specifications, will serve communities for over 100 years. Now that's engineering for the ages. Our final stop takes us to Gabis Al-Balad Wire Rope Factory, where they're manufacturing specialized wire rope for drilling operations, equipment that's been fundamental to oil exploration since Colonel Drake drilled the first commercial well back in 1859. NTHE process begins with wire drawing, where high-carbon steel rods get pulled through progressively smaller dies. Starting at maybe 5 millimeters diameter, the wire passes through 15 or more dies, eventually reaching the final diameter of around 2 millimeters. Each pass through a die work hardens the steel, increasing tensile strength to over 2,000 megapascals. That's stronger than most structural steels. Between passes, the wire travels through cleaning tanks that remove scale and apply lubricants for the next reduction. Next comes stranding, where individual wires combine into strands. A specialized stranding machine called a tubular strander holds multiple wire spools. As the machine rotates at high speed, sometimes 80 RPM, the wires twist together around a center wire, forming a strand. The lay length, or distance for one complete twist, is carefully controlled. NTHE closing operation is where rope takes final form. 6 strands, plus a fiber or wire rope core, feed into a closing machine, essentially a larger version of the strander. This machine twists the strands around the core, creating the finished rope. End-post closing treatment is crucial for drilling applications. The rope passes through a straightening die that removes residual twist and ensures straightness. Then it undergoes pre-stressing, where hydraulic tensioners apply loads near the rope's working limit, seating all components and stabilizing the structure. Finally, the rope receives lubrication treatment, special petroleum-based compounds that penetrate between wires, reducing internal friction and preventing corrosion. Finished rope gets spooled onto reels, ready to handle the punishing demands of deep drilling operations, where it might raise and lower thousands of feet of drill pipe countless times during its service life.